going back now to Friday, talking about some of the relationships that we already know from our work in chapter 2. In particular, in chapter 2, we did a lot of talking on how to calculate molar masses and how to go from those masses to calculating moles. That was basically the bulk of the calculations that we did in chapter 2. And then we threw in a little bit of wrinkle on that from chapter 7 here with the calculation of empirical formulas and mass percents. Well, now the only thing that's different is that we've got to incorporate this concept of a mole ratio. And the mole ratio concept just tells us that if I have a balanced chemical equation, the balanced chemical equation is going to tell me what the relationship is between my variables, between my compounds. And I can use that as a ratio in a conversion step, just like I would use 12 objects in a dozen, 12 inches in a yard or in a foot, 3 feet in a yard, 1,000 meters in a kilometer. All of those conversions that we used for distance or volume in chapter 1, we can do in the same kind of way here with mole ratios using the balanced chemical equation to tell us, okay, for every 1 mole of ethane, I'm going to need 4 moles of oxygen to get it to react. Now, one method of organization is through something that I refer to as the mole map. And what the mole map tells us is it gives us a way of doing inner conversions. And if you look at it from this standpoint, we actually saw a version of this back in chapter 2. We didn't have this part, we didn't have this back end, but we definitely had this part of the map where we could interconvert between mass, moles, and particles. And really all that is different here is now we have 2 of those maps. Again, mass, moles, particles, mass, moles, particles. The thing that we didn't have before that we now do is a bridge. The bridge between the 2 are the equation coefficients from that balanced chemical equation. So there I've got my bridge. And now I can connect one substance to another if I have a balanced chemical equation to work from. And so long as I have that, I'll be in good shape. And so this is largely the subject of your lab this week. If you haven't done it yet, if you're in the Wednesday, Thursday group of your hybrids, this is what you're going to be doing in lab either this afternoon or tomorrow, is you're going to be playing between aluminum and copper sulfate. And the thing that ties those 2 substances together is the fact that they react with each other and that there is a specific ratio of reaction that comes from that balanced chemical equation. So let's do some examples here. I've got 13.33 grams of aluminum that I'm going to burn in excess oxygen. What mass of aluminum oxide would be reformed as a result of this reaction? Now, in order to do this equation, to do this calculation, there's something I'm going to need first and foremost. And that something is a balanced chemical equation. I've got aluminum reacting with oxygen to create aluminum oxide. Now, my balanced chemical equation, when this is all said and done, is going to look like this. That's my balanced chemical equation. That says that for every 4 moles of aluminum, I'm going to need 3 moles of oxygen, and I'm going to get 2 moles of aluminum oxide. I want us to keep this in mind as we start to walk through the process. So there's my balanced chemical equation. Here's what I need to do. I have 13.33 grams of aluminum, and I want to turn it into some amount of aluminum oxide. If I follow the map, I can see that I'm starting here, mass of aluminum, and to get to where I want to go, mass of aluminum oxide, I have to follow the arrows. I can't just go straight from one to the other by comparing molar masses or anything like that, because there's no set guarantee that they are reacting in a one-to-one fashion. If we look at the balanced chemical equation, we can see that they are not being enacted in a one-to-one fashion at all. So I've got to go through the map, which means I've got to go from grams up here to moles. I've got to go from moles of aluminum over to moles of aluminum oxide. And then I've got to go from moles of aluminum oxide down to grams. So that's my game plan overall. Now the mole map tells me how I'm going to get there in terms of, in this step, you're going to use molar mass. In this step, you're going to use the equation coefficients. In the last step, you're going to use molar mass. And that's fine and good. But I can also see that out of my labels as well. I'm going from grams of aluminum to moles of aluminum. So I know that my conversion factor is going to have grams in the denominator and moles in the numerator. And I can follow that logic kind of the rest of the way through. So if we follow this map, as I mentioned, we're going to end up converting mass of aluminum into moles. We're going to convert the moles of aluminum into moles of aluminum oxide. And we're going to convert the moles of aluminum oxide into grams. We can do all 3 of these steps at once using dimensional analysis. And by doing dimensional analysis, we will avoid some rounding errors because we'll be doing all the calculation steps all at once instead of calculating the first step, rounding it, calculating the second step, rounding it, calculating the third step, rounding it. Remember from chapter 1, each time we round, we introduce more set of error. The more error we introduce, the less we can trust our results, the less accurate they become. So let's go about solving that problem then. I have 13.33 grams of aluminum. My first step is to convert the grams of aluminum into moles of aluminum. For that, I need a molar mass. Molar mass of aluminum, 26.98 grams. Now I'll get my grams of aluminum to cancel. My second step, I want to get rid of the moles of aluminum. So moles of aluminum in the denominator, moles of aluminum oxide in the numerator. This is where those coefficients come in. 2 aluminum oxides for every 4 aluminums. My moles of aluminum cancel. Last step, I need to turn the moles of aluminum oxide into grams of aluminum oxide. Again, we're going to need the periodic table for that. Aluminum oxide has 2 aluminum, so 2 times 26.98, and 3 oxygens, 3 times 16. 1 mole is 101.96 grams. My moles of aluminum oxide cancel, and I now just have grams. So everything's canceled out except for the grams. I can do my calculation, 13.33 multiplied by 2, multiplied by 101.96, divided by 26.98, divided by 4. How many significant figures should I have? 4. I started with 4. All my mass calculations at least have 4. This is an exact ratio, so it does not play into it. 4 sig figs would be 25.19 grams of aluminum oxide. All right. Any questions regarding this example? All right, then let's look at another example. How much carbon dioxide enters the atmosphere annually from the combustion of 6.8 times 10 to the 12th kilograms of carbon? Okay, now we're talking about the combustion of carbon. So that would be carbon reacting with oxygen to give us CO2. The process here is going to be remarkably similar to the one that we just did. I'm going to start with my 6.8 times 10 to the 12th kilograms of carbon. Now, when it comes to kilograms, molar masses, I can do one of 2 things with. Since we are doing a conversion here, so long as my mole to mole ratio has the same units, I have a lot of degrees of freedom, so to speak. And so one of the things I can do is, if 12.01 grams of carbon is equal to 1 mole of carbon, I can make the same argument that if I multiply both of those numbers by 1,000, I would get the same ratio. 12.01 kilograms of carbon is equal to a kilomole. And the balanced chemical equation says that 1 mole, 1 kilomole, whatever I choose of carbon would have an equal amount of carbon dioxide on the other side. The 1-to-1 ratio holds regardless of what label I put in front of that mole. So with that in mind, instead of doing the first step of going, okay, I need to turn kilograms into grams and then grams into moles, instead of doing all of that, we're going to simplify a little bit. 12.01 kilograms of carbon and 1 kilomole of carbon. That'll get rid of my kilograms. My mole-to-mole ratio is 1 to 1 to 1. So 1 kilomole of carbon gives me 1 kilomole of carbon dioxide. And the same kind of logic would apply to the molar mass of carbon dioxide as well. 1 kilomole of CO2 would weigh 44.01 kilograms. Now, you'll notice in this circumstance that because our ratio here is 1 to 1, this is one that can be solved with a direct comparison of the molar masses. And that's really all that we have to do. Multiply by the mass of the product, molar mass of the product, divide by the molar mass of the reactant. That isn't always the case. That's why we have the map to kind of organize ourselves appropriately. 6.8 times 10 to the 12th times 44.01, divide by 12.01 to two significant figures. I get 2.5 times 10 to the 13th kilograms of CO2. So we could have converted all of this to grams, solved it for grams. We would have got a big number. We would have got 2.5 times 10 to the 16th instead of times 10 to the 13th. The nuts and bolts would have been exactly the same though. All right, any questions with this example? All right, I want you to try this one on your own. Again, giving you the balanced chemical equation. We're looking at carbon dioxide production here coming from methane, natural gas, this time instead of coal. How many kilograms of carbon dioxide are released into the atmosphere from natural gas power plants? This is based on 2014 data. So go ahead, go through the process, try to solve this here. I'll walk around and try to help you out a little bit. All right, it looks like most of you are in the right spot with some sig fig issues maybe, or if you couldn't see the periodic table, it was a little bit hard to get to the molar masses. But the end result here is that you should have got something in the neighborhood of 6.0 times 10 to the 11th kilograms. Again, where you ended up kind of depended on a couple of factors. First and foremost, you had to be able to get the correct molar mass of methane, which would have been right around 16. because you have a carbon, which is 12, and 4 hydrogens at 1 each. So 12 plus 4 is 16. The 0.05 comes from those little add-ons, the 0.01s on each of those elements. And then the 44.01 you should have got from the previous example because we used carbon dioxide there as well. 1 carbon plus 2 oxygens is 44. So this should have been where you ended up. All right, any questions with regard to this example before we move on to a new topic in this chapter? Okay, this is another feature that you're going to see in that lab if you have not been to lab yet. It's the idea of yield. Now, when it comes to yield, we will often refer to the effectiveness, the efficiency of a chemical reaction by its percent yield. Its percent yield is the ratio of what is called actual or experimental yield and theoretical yield. Now, the theoretical yield is the maximum amount of product that can be produced. This is predicted by stoichiometry and is backed by your law of conservation of mass. That's the maximum amount that you can make. If I start with this much reactant, it's going to have to give me this much product. It can't give me any more because then I'd be inventing matter in some kind of way. But if it gives me less, then we can start talking about where the less comes in. And so that's where your actual yield comes in. Theoretical yield, stoichiometry says this is what I should get. Actual yield, you do the experiment and this is what you actually get. And the two should be compared to each other for percent yield. The closer it is to 100%, the more efficiently, the more well run that conversion is. Doesn't mean necessarily that it's, a perfect reaction, but it does give us an idea of an efficiency rating. If our yields are greater than 100%, then we have to start and we have to go back and look at, well, we made a mistake somewhere. Did we make a mistake in our calculations? Did we make a procedural mistake? Like, if something's collected in water, did we dry it enough? Or if we combined it with another solid, did we get all the other solid out? Because all of those things would add weight. If our yield is low, what did we see? Well, I can see that it didn't all react. Well, I can see that a bunch of the product is stuck in the solution and I can't get it out. Can't filter it, goes through the filter. Too small. So we start looking at things from an experimental standpoint when we have error issues, high or low. The thing that we want to avoid are two things. We're talking about errors in experiments. We never want to say that we made a calculation mistake, because if I made a calculation mistake, the first question that any reader would say is, well, if you know that you made a mistake, why didn't you fix it before you made the paper? Reasonable enough question. The other thing is, we don't want to talk about human error. Human error is a generic kind of descriptor. Doesn't mean anything. Especially Students tend to use it as a catch-all. I'm a human, therefore I made errors. And that's really not what we're getting after. You can talk about instrumentation, you can talk about procedure, you can talk about a lot of different things. If you did make a mistake, you should be able to tell how you impacted and made that mistake. So I did this, which was wrong, and this is how it affected the procedure. This is how it affected the error. I was supposed to heat it for 15 minutes. I heated it for 10 minutes. My yield came out lower because I didn't let it go long enough. That's realistic. That's also tied to procedure. It's not just tied to, oh, I did something wrong. Another question. If 18.2 kilograms of ammonia is produced by the reaction mixture that initially contains 6 kilograms of hydrogen and an excess of nitrogen, what is the percent yield of the reaction? So we've got two things here. First, we are told how much ammonia was produced by the reaction. This would imply an actual yield, not a theoretical, an actual. We did the experiment. This is what we got. To find percent yield, what we need is actual yield and theoretical. To get to theoretical, we're going to have to do some stoichiometry. For the stoichiometry, I start with my 6 kilograms of hydrogen. I know that there are 2.016 kilograms of hydrogen in every 1 kilomole of hydrogen. Now I go to my reaction equation. 3 kilomoles of hydrogen for every 2 kilomoles of ammonia. My kilomoles of hydrogen cancel. One kilomole of ammonia weighs 17.03 kilograms. So if I do this calculation, my theoretical yield, 6 times 2 times 17.03 divided by 2.016 divided by 3 to 3 significant figures, 33.8 kilograms of ammonia. So this is my theoretical yield. Again, stoichiometry gives us theoretical yields. To do percent, I need to take actual 18.2 kilograms divided by theoretical 33.8 kilograms and multiply it by 100%. 18.2 divided by 33.8 times 100, 3 significant figures, 53.8% is my yield. So this is not a terribly high yielding process. And this is actually quite common for the ammonia making process if we do ammonia making at lower pressures. Do it at higher pressures, it's a process called the Haber process, and that one's a lot more efficient, especially once we do a couple of other things to help kind of boost it along. All right, any questions here? All right, so we've got one final concept that we want to go over. And really, this final concept is an extension of what we've just been talking about for the last half hour. In all the example problems that we've done, we've mentioned that one of the reactants was in excess. And that meant that we knew that if the other one doesn't run out, that whatever amount of the reactant that we were looking at was going to undergo a full conversion. But what if that's not the case? Let's go back to this charcoal example. I've got carbon, oxygen, and I'm going to make carbon dioxide. If I took a charcoal brick, lit it on fire, held it up in the air, and started walking around campus with it, what is the most likely scenario? That I'm going to consume all the oxygen on campus, or that eventually the charcoal brick is going to run out? Eventually the brick runs out. Take that same scenario. I light that brick of charcoal on fire. I put it into a spaghetti jar and close the lid. What's more likely to happen? The oxygen inside the jar goes away, or the carbon burns up? The oxygen goes away. So we understand the idea that a chemical reaction has its limits. And those limits are based upon the reactants themselves. When one of the reactants is no longer present, the reaction stops. Now, how do we apply this to other kinds of scenarios? Well, what we're talking about here is something called a limiting reactant. A limiting reactant, by definition, is the reactant that runs out first. And because it runs out first, it is the reactant that ultimately is responsible for how much product is made. Because when the limiting reactant is gone, the reaction stops, and that means that we stop getting product. Any reactants that are left over after the limiting reactant is gone are said to be excess reactants. And so some amount of each of those would be left over as a result when the reaction is finished. Now, in the event that I actually have exact amounts of each, and both reactants or all three reactants, however many reactants there are, all run out at the same time, what that is called is a stoichiometric amount, meaning I've added exactly the correct amounts of each of the reactants to the point where all of them react and all of them are gone when the reaction is over. There are no leftovers. There are no excess reactants. Stoichiometric amounts are kind of difficult to come by because you have to do the calculations ahead of time, and then you have to proceed with what would be close to 100% efficiency. No side reactions, no unreacted stuff afterwards. Kind of difficult to do, but in certain situations, definitely possible. As we go to think about the calculations here, I want to bring up an alternative analogy. This is kind of a fun one. Let's say, for the sake of argument, that after class here, we were going to go to Wendy's and we were all going to get cheeseburgers. Technically, bordering on impossible since they don't start serving lunch yet, but let's just roll with the analogy here for a second. Let's say that they've also lost their mind and they have decided that this is the only way to make a cheeseburger. And if I deviate from this, it's no longer that way. So in this very realistic scenario, we've got cheeseburgers that are consisting of a bun, a quarter-pound patty, a slice of cheese, 2 pickles, 3 onions. Can't deviate from it, no condiments. This is what it is. Under this scenario, if Wendy's was undergoing a major shortage, kind of like most places were somewhere around March and April, and this is all that they had on hand, how many of us could they serve? Take a second, try to figure it out. Each cheeseburger has a bun, a quarter-pound patty, slice of cheese, 2 pickles, 3 onions. All right, I've got an answer of 10.
4.
All right, who said 4?
Jacob.
Okay, Thomas said the same thing. I think you're misreading the second line. It's not a 1 1/4 pound patty. It's a quarter-pound patty.
Oh.
All right. All right, I'm hearing a couple of 10s. Anyone disagreeing here? All right. The answer is 10. Now, how do you go about doing that? Well, you just take each ingredient and you figure out how many burgers it could have made. So I look at the buns. I could have made 13 burgers with the buns. I had enough meat for 20 burgers. I had enough cheese for 25. I had enough pickles for 50, and I had enough onions for 10. And so with that logic, I know that I can only make 10 burgers as the recipe prescribed. Everything else was in excess. Now, the reason I bring up this analogy is because when we do limiting reactant kinds of problems from a stoichiometric standpoint, we're going to follow the same kind of process. Meaning, I have this much of reactant 1, this much of reactant 2. How do I know which one's the limiting reactant? I got to figure out how much product each one of them make. Reactant 1 makes 30 grams. Reactant 2 makes 50 grams. Reactant 1's the limiting reactant. 30 grams is the yield. Same analogy, same way of doing things, just using chemical concepts instead of these more tangible ones. So we're going to save this for Friday. I still want you to do the post lecture for tomorrow night, or yes, for tomorrow night. So I want you to do that. I think you've got the tools available. What I will do is there are 2 examples in here that I will put in as a supplemental on my YouTube channel that you can look at if you want to get a little bit of practice before you dive into the post lecture. But with 2 minutes time, I don't have enough time to do one of the examples, let alone both of them. So I'll put them up as a supplemental, view them up in your own time. Have a good afternoon.
Real quick, I just want to let you know I started class under a different name.
Okay, I got you, Jacob.
All right, thank you.